Hello. So we're into the last week of new material. So what we're going to be doing is we're going to be looking at the idea of what we call partial derivatives. And this just extends our idea of what a derivative is, but it's basically the same kind of thing as we learned before. We're going to learn what it is. We're going to learn formulas to get it. And then we're going to show that how using this, we can find maximums and minimums, just like we did before. So we're going to go at a quicker rate than we did before because, last time we took a whole chapter to get there. Now we're just going to take 3 classes. But because you've seen it before, it's the same kind of thing. So hopefully the actually new material that's kind of challenging to the mind isn't that great. Okay, so let's think about how we would do a derivative in our new multivariable situation. So recall what we have. We have some kind of landscape of hills and valleys that, we've got our 2 inputs, X and Y. That gives us a place on the map. And then the output gives us the height. So that's why we have kind of like a terrain. So how can we get a derivative? Well, we know that already. What we know is that we just restrict it to one variable at a time. And if you think what that is, then that'll tell you the answer immediately, right? If you take a terrain, it's kind of like a big cake. You slice it in the X direction. You look at each of those slices. When you look at it, it's going to look like that. So it's just going to look like a normal graph of a function. You can also go the other direction. So if you're cutting this way, you can cut that way as well. And again, you'll get slices that just look like a function. Okay? And so what you can just do, it's kind of like you have a direction. You're saying, how is the function changing in that direction, in the X direction? How is the function changing in the Y direction? And that rate of change in that direction is a derivative, and we know how to handle those. Okay, so here is the slide of technical details. Okay, so we've got a function. It's a function of 2 variables, X and Y. That means it has an X derivative and it has a Y derivative. And we call them partial derivatives, right? Because the derivatives is really both X and Y. So we just look at part of that. We look at the X part and we look at the Y part. And we kind of have, so if we're going to have some notation. So what we do is we look at F. And then if we put a little X there, that means we're thinking of it as X varying. That's the partial derivative with respect to X. We also have a partial derivative with respect to Y. And the definition of it is it's exactly the same, right? It's the rate of change of F with respect to X. And we'll start off by just basing ourselves at a point. So, and a point, it has to be both the X value and the Y value. So a point, remember, is an X value and a Y value. So it's given by a pair like that. And we see that it's exactly the same definition that we saw before. And the same with the derivative with respect to Y, right? What you do is you fix the other variable, so that never changes. Here A is the same all the way. And we just see what happens as B varies by a little bit that much. Whereas with the partial derivative with respect to X, we kept the Y variable fixed. And we let the X vary a little bit by a tiny amount. Now we do it like this, but we know there's other ways you can do it. You can put the point in the middle. That'll give you your best estimates. You can put it at the other end. As long as your tiny interval contains the point A, B, it'll give you an estimate of what that partial derivative is. And the way to get good estimates is to use a small interval. And if you put it in the middle, it'll converge even faster. Okay. And so that's what happens when you do it at a point A, B. But then as A and B change to different values of X and Y, you get a function of X and Y, just like the derivative is a function of X when it's in one variable. In two variables, it's a function of two variables of X and Y. And so you have this F with a subscript X and F as a subscript Y. They're the two partial derivatives of F. Okay. And so we're going to spend today and tomorrow just kind of like examining what that means. And we're going to end up being able to come up with formulas for that. So remember, just like with normal derivatives, remember we had F prime and we had, terrible F, isn't it? We had dy dx with two different ways of writing down a derivative. Oh, well, here we have two different ways of writing the derivative. So the convention is that you use a different kind of d for partial derivatives than you do for normal derivatives, just so you don't get confused between the two. Right, so this is the full derivative. So there's only one thing that's varying. Here in the partial derivatives, you've got a choice of two things that can vary. So that's why we put it like this. Okay. Oops. Why does it want to show everyone? Okay. And straight away we can the simplest example is the linear situation. So let's say we're selling shirts and jeans, right? And so we get revenue from in our store, and we sell, I don't know, we sell shirts for $10 and we sell jeans for $25. Okay, then that's a nice revenue function. So we've got a partial derivative with respect to x and a partial derivative with respect to j. Okay. And to do the partial derivative with respect to s, with respect to shirts, what do? Well, we vary shirts, so we have 10 s plus a little bit. So let's have a delta s over here. Plus 25j. Okay, we're keeping the amount of fixed jeans we sell fixed, and we're going to subtract 10 times s plus 25j. Right, that's how we do a derivative. Well, if we go through this, we get 10s plus 10 delta s plus 25j minus 10s minus 25j over delta s. We're just doing a rise over run. See, the 10s's cancel, the 25j's cancel, the delta s's cancel, and we get 10. So the partial derivative with respect to s is 10. And what does that tell us? That means, well, what does a derivative mean? It means that for every shirt we sell, we get 10 extra dollars. Well, that's obvious because we're selling the shirts for $10, right? What's the partial derivative with respect to j going to be? 25, right? Every time we sell a pair of jeans, we make $25. Okay, so that's what it is in the linear case. But we knew that already. We know that derivative is the same as slope, rate of change. So everything that you know about derivatives remains true when we go to multivariable case. Okay. Okay, so we've talked a little bit about how you write down what a partial derivative is. You've got two notations. So let's think about a situation. So this is a linear situation, but of course, where derivatives become interesting is when there's a non-linear situation, like this. So here's a scenario we've visited a lot of times, and that's the idea of putting a drug into somebody, because we know that what happens is the drug goes up as it's injected, and then our body secretes it, and the drug breaks down and it decays away. So it's kind of like an interesting scenario because it's got a nice peak to it, like that. So it's a nice function to think about just as a function. Okay. Here we're thinking of it as a function of two variables. This time the inputs are how far away the site is from the place of injection. And the other one is going to be the time. So if you think about, you take a patient, you inject a drug into him, and you've got sensors at different parts of the body. All right. And how much drug is there is going to be a function of how far away you are from the injection site. Right? Is it at the tip of my fingers or the tip of my toes or in my ear or whatever? So it's the distance that it has to travel in the body. And time. Okay. So for instance, if it injects it into my arm, that's time 0. At time 0, there's going to be no drug in my ear, obviously, right? All the drug is going to be at the site. And as the time goes forward, the drug spreads all through the body, reaches a peak, and then will decay away. So let's just think of these partial derivatives. And let's think about what the units are, because as always, units are very useful because they kind of help you explain what the thing actually means. From that, you can then get a interpretation and a practical interpretation of what's going on. And then, as usual, the thing that we're always interested in is the sign. That's like when you talk about the derivatives, the basic thing you can talk about is the sign of the derivative, because sign is positive, means it's increasing. Sign is negative, means it's decreasing. Sign is 0, means that it's not changing. It's just the most basic thing you can say about a function. Okay, so let's think about dc dx. Okay, what is that? That's the change in concentration with respect to how far away you are from the injection site. So firstly, let's do units, dc dx. Okay, it's going to be units of c per unit of x, like how we do any of these problems. Okay, what's units of c? Doesn't tell me what the concentration. So it's so what's a unit of concentration? It's kind of like something like milligrams per milliliter, right? Is a typical kind of thing for a thing. Per, and what's the unit of x? It's millimeter. So we can put these together. It's kind of like milligrams per milliliter, millimeter sort of thing when we put them together. Okay. What is its interpretation? It's the amount, the concentration of the drug, depending upon how far away you are from the injection site. Okay, is this going to be an increasing function or a decreasing function? The further away from the injection site, is the concentration going up or down? It'd be decreasing, right? All right, we put the drug in. Here is going to have more than there. Okay, so it's going to be negative. Next we have dc dt. Okay, again, that's units of concentration per unit of time. So it's milligrams per milliliter per, and time is seconds. Okay, so that's good enough. Okay, what does it mean? It's telling what is the concentration, how is the concentration changing over time. Okay, so I put a sensor here, I put the injection in. Is that going to be increasing or decreasing? Let's just talk about it initially. Is it going to be increasing or decreasing?
It's going to increase initially.
Yeah, it's going to increase initially, so it's going to be positive. Of course, much further down the line, the drug's going to start getting taken up or whatever, it's going to go down. But that's the basic scenario. Okay, so that's kind of how you analyze a situation using partial derivatives. We've done this before, okay? We did this with one variable, now we've just got two variables to worry about. Okay, so remember way back when we first did derivatives, I asked you find a derivative. So you had to come up with a number. And remember, there's always basically been three kinds of problems that I've given you. One is I give you a numerical problem. One is I give you a graph. And I ask you to get the numbers from that. And the other is I give you a formula. Okay? So let's think about a numerical problem here. Okay, so this is some kind of exercise. You know, this comes from health and exercise science, this kind of data, right? So rollerblading. People still rollerblading? Sometimes you see them, okay? But if you think about it, if you're going out to do some exercise, you go in the park, you're rollerblading, you're burning up calories, right? So that's what you're doing it for, trying to keep trim. And it's going to be a function of how big you are, right? Because obviously the bigger you are, the more effort you've got to do to get yourself moving, and also of how fast you're going. So to go really fast, you've got to put a lot of effort into it, right? And so obviously it's going to be an increasing function of both of these things, right? And we see that from the table. We go in this direction. As we increase speeds, we see that we're burning more calories. As the person becomes heavier, they're also burning more calories. Okay, so that's an initial thing. And we know what the units are, right? So this is going to be calories per mile, calories per minute per miles per hour, and calories per minute per pound. Okay? So the calories per minute per mile per hour tells you, as you go faster and faster, how much more additional calories you're going to be burning per minute. And calories per minute per pound tell us how much additional calories per minute you're going to burn as the weight of the person increases. Okay, so this is actually just the same problem as that we've done before, except it's now a two-dimensional problem. Before, I'd only give you a table in one dimension, right? There'd be only one row or there'd be one column. And you just go along the row and you would do rise over run. This is a two-dimensional problem in the fact that you've got rows and you've got columns. And if you do the row thing, then you're doing the partial derivative with respect to miles per hour. And if you do a column difference quotient, you're doing the partial derivative with respect to weight. So this is really, we've done all this before. Okay, so let's go ahead and do a problem. The same principles apply. We try to get the interval as small as possible, and we try and put our thing in the middle. So let's do FW 160. Okay. So this is a 160-pound person going 10 miles per hour. Okay, so the first thing we do is we find the thing. We find 9.2. Oh, 9.2 calories per minute. That's enough. It's a candy bar. Thousands of calories. Anyway, so what does this mean? This means that a 160-pound person going 10 miles per hour on their rollerblades is burning 9.2 calories per minute. So now I want to figure out what W 16010 is. So what's happening? So weight is varying. Weight is varying. Weight is varying. So that means we're in a column. We're stuck in a column. Right? So we're going 10 miles per hour, and we want to figure out if someone weighs an extra pound, how many more calories are they going to burn? Okay, so we want to do, so we take our point, we take an interval as small as possible, and we make it the midpoint. So we're looking at these two values here. Okay. So we're going to get, what is it, 10.2 minus 8.3 over 180 minus 140. And now that's for the calculator. What's that? That's 1.9 divided by 40. So that's around what? It's just a little bit less than a 20th. So it's around 0.05. 0.05 what? It's 0.05 calories per minute per pound. Okay, so the person weighing 160 pounds, going 10 miles per hour, if they kind of put on a 1 pound weight, they would be burning an extra 0.05 calories per minute by wearing that weight. So, you know, sometimes people put weights on themselves when they do exercise so that they burn more calories. Okay, we can ask, what is FS? 160.10. Well, this time we're in the row. Okay, and again, we do the same thing. We want a midpoint. We want it as small as possible. And so now we get 10.8 minus 7.7. And now it's what? 11 minus 9 equals, what's that? 3.1 divided by 2 is 1.55 calorie per minute per mile per hour. What does that mean? That means we've got our 160-pound person going 10 miles per hour. If they were to increase their speed by a mile per hour, they would be burning an extra 1.55 calories per minute. Okay, so this tells us, what does this tell us? We do 1.55 divided by 0.05, that's like 31. So it's 31 times harder to go an extra mile per hour than it is to carry an extra pound. So the equivalent of, you know, going an extra mile per hour is to like maybe put 31 pounds on you to get the same amount of effort. This is exactly what we've done with derivatives before. Okay, so the whole new thing is that it just have to go in 2 dimensions. If it was a 3-dimensional problem, then our table would be kind of like a cube, and then we'd have 3 directions to go. But of course, it's difficult to visualize a cube of data, so that's why we're just doing it this way. But it's exactly the same kind of scenario. So we know what the numbers mean. Okay. The important thing is they're positive. So that tells us it's increasing, right? So more weight, more speed means more calories burned. The size of it is the next important thing. So it allows us to compare the two things. So we can do, again, this is exactly something that we did when we looked at the just normal derivatives, right? We did this kind of linear approximation of using the derivatives. Well, we can just add up the change. There can be a change in the x direction, there can be a change in the y direction. So in this scenario here, you know, we can estimate how would a 165-pound person going 10.2 miles per hour, we could estimate that, right? We could estimate that as take our data point that we know what it is, that's 9.2. Then we've got the effect of weighing 5 pounds more. So that would be 5 times F weight, right? Which is 5 times 0.05 plus the effect of going faster, so that'd be 0.2 times F speed, so 0.2 times 1.55. So that's the kind of stuff we did before. So this is what we're doing here. So the change, when we've got two variables, we can approximate the change as being the change that's due to x changing and the change that is due to y changing. And we can just add them together, add the two changes together. So let's say, for instance, we know F 120 is 2,750. We know that change in x at that point is exactly 4. So it's an increasing function of x, and it's an increasing function of y. We want to approximate that. So we need our base point. So then there's the change with respect to x. Well, the rate of change in the direction of x is 4. How much do we change by? We change by 5. So, hang on. Delta x times fx. 20 delta y 120. Let's just fill it in as steps. So that is F 120 is 2,750. Our delta x is 5. Our rate of change in that direction is 4. Plus delta y is 1. Our change in that direction is 7. So we start off at 2,750. We add 20 because we're going 5 units in the x direction. And we add 7 because we're going 1 unit in the y direction. So the total change is 27. So that's the total change in going from here to here. And we just add it to our old. So we get 27.77. That's our estimate. Okay, and all the old caveats from before hold, right? The closer we are to our base point, the better our estimate is going to be. The further away we are, the more likely we are to be nervous about it. Right? But this looks like okay. This looks like, but if I was to ask for F200, 100, you'd be a little bit nervous because you'd think, oh, that's too far away to be actually much practical good. But this is good. Okay. So let's we know that, say we have some function of two variables, and we know the partial derivative with respect to x is positive, and the partial derivative with respect to y is negative at our base point 2, 3. Which one of those two tables is consistent with that? So as we're going in the x direction, what are we expecting to see? Increasing. Is this increasing with respect to x? Is this increasing with respect to x? Yeah. Okay, so that the partial derivative with respect to y is negative. What does that mean? Decreasing. So is this decreasing as y? No, it's increasing. What about this? Yeah. This is a better candidate. And because we didn't even have to look at 2, 3 for the point, right? But 2, 3 is this point here. We definitely see that the partial derivative at 2, 3 is kind of like 20 minus 12 divided by 4 minus 2. Partial derivative looks like 4 to me. Over here, minus 8, it looks like minus 2 to me. Yeah, that one's definitely go. We can do the same thing that we do with tables. We can do with contour diagrams, right? Because the partial derivative with respect to x, well, it's like taking a cross section like this. So it's looking at the landscape, and you just say, in the x direction, am I going uphill or am I going downhill? In the y direction, am I going uphill or am I going downhill? So let's have a look at the point Q. So the partial derivative with respect to x, I'm going from 7, I'm going in this direction, and it looks like I'm crossing the 5 contour. So as I go in this direction, so I'm going from 9 to 7 to 5. So what can you tell me about the partial derivative with respect to x? F is decreasing in this direction, so the partial derivative with respect to x is what? Positive or negative? Negative, right. Because it definitely looks like we're going down. So it's going to be either C or D. Next, we take the partial derivative with respect to y, and that's the same as going in this direction. Okay, and so now what's happening? We go 9 7, 5. So is it positive or negative? Negative, yep. So at this point here, if we go this way, we're decreasing. We go this way, we're decreasing. Both partial derivatives are negative. We could even say, well, which one is going to have bigger magnitude? How do we determine that? By how close the lines are together, the contours are together, right? Contours bunched up means steep. Contours spread out means mild slope. Okay. So when I go in this direction, right, I've got this kind of spacing between the contours. Okay. So I could, if I actually had my ruler, I could find out that what this distance is, and then I would do 5 minus 9 divided by that distance. I could actually come up with an estimate for that. Going in this direction, now my fingers can't fit between it. It's kind of like here. Right? So it's I have to put these on up. So it's going to be 9 minus 5 divided by that. So since it's a bigger distance, when I divide by it, it's going to be a smaller number. So the derivative in this direction has bigger magnitude than the derivative in this direction. Oh, it's just the same one, right? Okay, so let's list the points PQR in order of increasing f of x. So f of x is horizontal. So I take out my ruler. I'm going to compare this. Right, so as we said, this goes down by this amount. So this is quite sharp negative. Okay. When I look at P, what happens here? Here is my contour 7. 7's over here. 9's over here. So it's kind of hard, but I can imagine that there is a 6 contour around there. Okay, so I think it's going over this distance here, it's going from 6 to 7 to 9. So it's increasing, but it's not increasing very steeply. Okay, so P definitely comes after Q. We look at R. Look at R. What's happening at R? R looks a bit like P, doesn't it? Here is 1, there is 1, there is 3. Okay. Hard for me to decide which one is higher, but I'm thinking P is right, because this distance here is smaller than this distance here. So I would think that it's QRP. Okay, so it's just taking a ruler, keeping things horizontal, where you examine it just in that direction. Anyone got any questions? You're not looking that scared of this. You're kind of looking at it. Okay, good. It's not that scary, right? So let's actually try to come up with an estimate for a partial derivative. Okay. So let's have a look at the point 2, 1. So here is the point 2, 1. and we want to figure out what is the derivative in this direction. As always, it's rise over run. So we're going in this direction here. So we see it going from 28 to 27 to 26. It's going to be negative. All right, so we're going to take 26 minus 28. That's the rise, right? And we've got to figure out over how much distance that happened. Going from there to there looks like to be around 3 units. Everyone okay with that? Minus 2/3. Different point, 1, 2. So now this is this point here. So maybe I'm thinking, so what do we want? We want things in the middle as close as possible. So I'm thinking I'm going to do that to be my estimate. So it's going to go down from 27 to 26. And the distance looks like, take my thing here, it's just a little bit less than a unit, so maybe it's like 0.8, it looks like to me. So it is what? It's minus 1.8, which is minus 5/4. Okay, so again, I recommend having a nice plastic ruler that can measure things. You can get good answers for this. Here's a little bit more exotic looking map. What do we got here? So we see 2, 3, 4. So we see like a little hill there. And 1, 0, minus 1, we're seeing a little depression here. At which of the following points is one or both of the partial derivatives approximately 0? Okay, so it's asking at which points are the partial derivatives, one or more, is the function basically flat? Okay. So if we look at 1 minus 1/2, oh, look at that. In the x direction, it's following the contour. All right, so f of x, df dx, in this direction, df dx is basically 0 because it's hugging the contour. Partial with respect to y is not. It's definitely not. It's like when you go perpendicular to the contour, that's when you're following the steepest line. Okay, but fx for that one. What about this guy? Negative 0.4, which is around here. 1.5. So it's around here. Okay, so going in this direction, definitely not 0. Going in this direction, it's not doing very much, but it's definitely not 0. So basically, this is just saying at those points, do you think the vertical or horizontal line is tangent to that contour line? Okay, that's enough for today. What we'll do tomorrow then is we'll start looking at formulas and turning formulas of functions, finding the formulas for the partial derivatives. And it's going to turn out to be exactly the same as we did before. Okay.